last session for today on airborne wind energy, and I think we will start now with Dylan Eijkelhof reporting on the MegAWES framework, and that's a term that you have heard several times already, so this is a development that Dylan started with his master thesis and has now really spread also to different groups, been picked up for various purposes. I'm sure we will hear something about this today. Go ahead.
Thank you. Thank you all for being here in this last session before the weekend starts for real. I'll be talking today about the collaborative open source modeling with MegAWES in the IEA Wind Task 48 or Workpackage 2. Basically, it is a collaborative framework anyhow, but I think it fits very well in the goals of the Wind Task of the IEA due to the fact of this collaboration that we've shown with multiple universities. You've seen many presentations already about the subjects. I will shortly go through them again, and also through two of the master students I'm guiding at Delft, which have been making very nice improvements to this model that I could not do, so I'm very glad that they did. And yeah, I will go through these topics. I start with a little bit with my introduction, like what is MegAWES? And MegAWES actually started during my master thesis, so this is back in 2019. I was at the time at ETH Zurich, and I got into contact with Roland to start my my master thesis on airborne wind. And I got to work with Uber and Faso, and yeah, we started to think about this meshing framework where we could design a kite and eventually do the dynamic simulations and then see for a megawatt scale what that would produce. And this is what came out of it. It took a bit more work than just my master's thesis. Part of it went then, and then we improved the dynamic simulations afterwards in like 1.5 years after. I'll show you a small video of it plays. Yeah, so basically this is one of the results that you can get out of the simulation framework. It's a kite flying. It flies, in this case, figures of 8. I will talk later also on how we updated this now with this, a different controller, but it's using the Sebastian Rapp controller, which he implemented during his PhD. And I modified it slightly for the retraction phase because I encountered some problems at the size that I was flying. Basically, the main problems I encountered were with the tether. There was a snapping effect, because basically you would fly back too fast, the winch could not deal with that, and you would have a sagging tether. And the minute you got back to this point where it's now, you can actually see it's sort of sagging. You can see it's not a straight tether at the moment. But what happened in this size is that the forces were so big that the minute it's straightened out, so the kite would start to turn, and the winch would still be reeling in. At some point the tether is straight, and you get a spike in tether force, and basically simulation stopped immediately because this would rupture the tether. So we had to slightly modify the framework, but apart from that, it's Sebastian Rapp's controller. It's a fully, like an autopilot, basically. It tracks, has a navigation module and a controller to follow it. So basically everything is dependent on the module itself. I'm not prescribing, like I'm prescribing a shape for the path, but not the actual path. So the amount of figures of 8 it makes is fully dependent on eventually reload speeds. And there is a maximum tether length that you achieve, and from that moment you will decide to go back into retraction. So the amount of loops is dependent eventually on what you choose as maximum tether length, and then reload speeds that are calculated based on the force. As this was implemented with a force tracking controller, that means during the traction phase you basically have a constant set point for the tether force, and the winch would decide to reel out or reel in based on this force. So you were trying to track a specific number. You have the forces of the kite pulls the tether, we have the dynamic model, and yeah, basically tries to track this, coming to the fact what actually includes in this model, which is the full thing is a dynamic simulation framework, but it's also the reference guide. So basically we published on GitHub, you can get the framework, it's there as at least the old approach, and hopefully after the summer we'll implement some of the later mentioned improvements to this. But it's a Simulink model, based on a ground station with a winch. So it has the dynamics of the ground station. There's a tether based on the Williams 2017 paper. It's this quasi-static tether model. It's already been mentioned once before, but we use it basically because it's much simpler to implement in this kind of framework due to the fact that you didn't have to use these very tiny time steps. And we were, in that case, with the time steps we were using, able to use the real stiffness of the tether instead of artificially reducing our stiffness, which also caused these numerical instabilities and longitudinal vibrations. So this tether model doesn't have these longitudinal vibrations in the tether, which is very nice. It converges to a steady state, and we have the forces on each side of the tether, and we can move on. There's the flight control, as I mentioned before. There is forces and moments. Right now we use static moments and forces, so basically I pre-compute the CL, CD curves, CM curves, and it's basically a lookup table. So based on your side slip and your angle of attack, you can figure out what the coefficients are, and you move on from there. Then there's the 3DOF and the 6DOF implementation. It was very interesting because we started off with the 3DOF because it was the easiest to implement for the kite dynamics. But basically what happens is you impose the orientations of the kite on the kite itself. But with the 6DOF, we're actually taking the inertia of the kite into account, and then actually we solve these problems of this tether snapping and all this other stuff, because the minute you have a sagging tether, the dynamics of the tether are not synchronized with the dynamics of the kite, and they basically do their own independent thing, and that led to this problem. And with the 3DOF, the kite responded much faster to whatever was happening on the forces, and we didn't see this snapping effect. So the switch was very important for us to learn that we had to change the model. So it is available on GitHub, so please find it there if you want to know more. It's fully implemented in Matlab/Simulink. We chose Simulink not because it has such great performance or speeds. We chose it because we wanted the model to be able to, we wanted to make it possible to be used by everyone. And the graphical interface of Simulink is just a very nice way to see what's happening, instead of you have to look in the code which modules actually communicate with each other. Now you can see physical lines going from one to the other, so you know there's interaction. That's why we chose it. So a little bit about the kite design. It's also been presented a little bit, so I'll go through it quickly. We have the full detailed design, so there's a complete finite element mesh for the kite is available. It is not used by the dynamic model because that's pre-computed forces, and we used it to actually do these pre-computations. So we used the actual structural model to first design the kite and eventually do fluid structure interaction steady state solutions that form our CL, CD, and CM curves. But the mesh is still available both in a Nastran file. Nastran is this it's a solver. You have MSC Nastran, or what I use is Siemens SimCenter Nastran. It's a commercial structural solver, but basically it's a PDF file, and it gives you all the grid points, how the elements work together, or how the elements connect, the materials that we use. They're all in the file, so you could open it and read it, because it's not in a binary format, so you can actually read what's in there. Twin fuselage, it's a single element airfoil, because at the time we didn't have the capability of using multiple elements, because I didn't have the implementation in the structural model. I do have it now, so I can use flaps, but at the time we didn't. So we have an aileron built in. It's one of the cutout sections on both outer sections of the wing. Then we have the twin fuselage, as I said. It has about a nominal power of 3 megawatts. It's a bit higher, but when you do the conversion also to electrical power, taking some efficiencies of the motor and the generator into account, you end up a bit lower. The surface area was 150 square meters. This was sort of like where I started off with. I had to make some fixed points, and I had the conversation with MPix Power at the time, and they couldn't give me any design for the AP4, so a megawatt scale, because they didn't have it. They didn't even have the AP3 built then. So I got the 150 square meter as a set point, and I started building the kite from there. It has a composite layout, so materials are actually laminates that are modeled inside the Nastran modules, and as I said, the full structural mesh. Then the collaboration, which is, I think, the most interesting part for everyone, is the fact how other people have been doing some amazing stuff with what I started with. And I'll start with one of the master students, which is Jesse Hummel. He's one of the control and simulation master students at TU Delft. And yeah, it's also one of the nice initiations of inter-department collaboration, I think, which we need for Airborne Wind as well. He started with looking at MegAWES, and he found out he wanted to implement a new flight controller, but then he found out that actually all the dynamics were a bit off. It was a bit strange what happened, and he figured out it had a lot to do with the winch. Because what happened with the winch, because we couldn't find any reference data, and wind turbine generators were way too heavy and or too high rotor inertia, mass inertias, we didn't really find anything. So what he did, he looked at it from a control perspective and started to do some stability studies on the winch by sizing it. So he had this sizing constant, which is basically the rotational inertia, divided by the radius of the drum, or the winch, because we assume it's one thing, squared. And basically he sized it, and you can see one of the figures. There's a pointer, right? Yes. You can see here, basically a parameter study of where he was sizing this sizing constant, so it's related to these two parameters, and then to a trim reload speed, which is eventually based on a wind speed. And I think he initially started with this 1/3 over, let's say 1/3 over the wind speed. Of the wind speed is the reload, so he did a parameterized study, and you basically want to be as much, because it's the normalized power output, you want to basically on this side. So what he then did is come up with this, it's a quasi-steady model of the MegAWES kite. So it is linearized around these given trim speeds, and then he analyzed the fraction of the ideal power that he could extract. And he did that so he could figure out, first for a kite without mass and then also for a kite with mass, he could figure out what would be the optimal tether force that you will want at a specific given trim reload speed, to sort of make sure that we didn't have these fast dynamics. As the old parameters you can see in the table, it was like a 32 kilogram meter squared mass inertia or rotational inertia. But then, once he started doing stability studies, he found out that much better parameters you get for the stability of these, to get more realistic dynamics of this winch, you get, well, almost 2 orders of magnitude larger. So basically the winch, when I started using it, was sized completely wrong. He did this parametric, so it's not an actual winch, so we have to see if they can actually be manufactured like that. But I think it's a much more realistic parameter to be using, which improved the stability of it. He verified this with the 3US simulations, and he found out also with higher and lower parameters that you had more or less power or very poor controllability of the winch and all this other stuff. Because what happens with the MegAWES kite, you can see high oscillations during traction phase due to gravity. At the outer sections, you have to reel in to pull the kite back up, which are all bad things. With this newly sized and controller base, where you find sort of, which I will come to, sort of optimal tether force that you will be tracking, so it's a varying tether force. He's able to get rid of these negative points for a similar case with the old controller. So that's what he did. So he basically has, what the original model has is a constant tether force, which had these large peak-to-peak differences. So basically during traction phase you fly through your pattern, and basically depending on which point you are in the, around the figure of 8, you would or produce power or actually extract power from the system, which is not that nice. And you have very high peaks, so basically you're oversizing your generator most of the time, which is not a good thing. So he did this study on a new one, so he started with a new winch controller, which is a feed-forward winch controller, and he has a kite tether force control. Kite tether force control is basically just a limit that you set. It's a value on the tether force from which you say, okay, actively now, or dump lift, or reduce the angle of attack, because we're ending up in too high tether forces. And then that basically sums up to about a similar, more or less similar average power, but with much less oscillations over the power. So the power quality improved drastically with this approach. And I think this is very nice, so we hopefully can implement this soon in the MegAWES one, so you actually have all the data. Of course, it can already be exchanged, but yeah, it's not yet fully published. We will publish this hopefully as well, but at least this master thesis will contain all the info. Then we have another master student, which is Nicola Rossi. He's actually trying to figure out what is actually the difference between the spiral and the figure of 8. So most of the studies that have been done on 2 different flight paths are usually different kites. So he wanted to do the same study, but then with the same kite, and then fly both flight paths, while at the same time just reducing the whole complexity of the controller. So moving back to the controller I also used during my master thesis. But he improved this by making it possible to fly a spiral. It's the L1 controller, so we had before a bit of the explanation of the, it was like more or less like an L0 controller. But this is using the L1, so you have a fixed L1 distance and you basically use it to track your flight path. And then eventually you go into a relin phase. So basically you have a spiral, and he uses the same approach also to fly a figure of 8. And then eventually he wants to use it to compare these 2 flight paths and see if it actually makes a difference on the same kite. Like what are the real differences? Are we having differences in power, or is it just a technical point that we want to do a different flight path due to tether twist, etc.? But I think it would be nice to see a good comparison. And he's developing a cost function for this too. So we will be optimizing both the figure of 8 and the spiral under the same conditions with the same kite. So we eventually can do a proper comparison. So yeah, this is then the figure of 8 with the same controller. Yeah, that's what he's been doing. And then we had the presentation also earlier of Niels. Basically, the University of Ghent has been a great user of the tool to do more high fidelity studies. And well, I'll go through it a bit quickly. You can see it also on the slide, but it's basically was presented just before, and I think many of you were there. But yeah, it's the fluid structure interaction of the kite, so putting them in high fidelity solution CFD, and eventually with URANS or hybrid RANS/LES solutions come up with the aerodynamic behavior. So then we also had, which was yesterday, we had Omid, who's also used it a little bit, but he kind of modified it more. So there were some issues that maybe some of the new implementations will solve, but also some issues that he had to solve himself. So basically, it turned out that the MegAWES was helpful in order to form some of the optimization problem, but also he managed to convert the Simulink model back to a Matlab file, or basically just Matlab code, to speed up and make it easier for optimization. And eventually also these lookup tables that I discussed, so made a polynomial expression or fit through this, so we have a continuous approach of that. And from what I understood, it's also the idea to eventually also make this available, and we might be able to in some way link it or put it in the same repository or have it somewhere, because I think it's very useful for other people also to be able to use this as a Matlab function. And then we had, I think it was also yesterday, Jean-Baptiste. He did the LES studies and basically also used the MegAWES reference guide. So you can already see a little bit why it was important for us to have this guide out. It's like with wind, it's way more normal. There are reference turbines, and Andrew made, I think, the first one, and then we moved on to some higher megawatt scale systems. It's used a lot, and you see here how useful this can be to another department. And yeah, so yeah, the wing modeled, it's an actual line, and so the wing was used in their studies there. And then there was also Nicolaas, who has been doing safety barrier function, I think it's called, including or safety filters. So basically, look at a winch or a controller that doesn't perform so well, and use then safety barrier functions to make sure you could potentially come from, once you exceed tether forces, go to a smaller tether force and have safe operation even though the winch is not performing so well. So that's where the MegAWES framework came in, but actually the simulation framework as well to demonstrate this difference. And that basically comes to the end of the framework. Of course, many of what I just said is not done by me. I think it would be nice if many of you would contribute as well. Come up with new modules, come up with extensions, better tether models if that's possible, or even what I'm trying to do is also better reference guides I think there's a lot to gain on a better reference guide as well. And thank you. And the link is on the slide, so if you want to go to GitHub, you can find it there. And yeah, thank you for listening.
So MegAWES is by now a real network operation, which is really nice. I think also proof that this IEA Wind Task is a nice tool to like spread the word and have many different people contributing. Are there any questions by the audience? Nicolas.
Yeah, obviously, I'm a big fan of the toolbox and stuff, which is why I've used it so much. And I was just wondering, moving forward, if you've had any thoughts about sort of the future, where you see this going, how you would like to take that sort of collaborative step to the next level, also in maybe like bringing together people's ideas and demands about what's needed next and where should we be going with this, and yeah, just some thoughts on the future.
Thanks for the question. I think this is pretty hard because I can, of course, not get other people to do something. But my ideas are at least to make sure that there's, what I'm doing now, for example, is also add modules and keep adding stuff as much as I can. So there's master students that improve the work. They create new winch controller and new flight controller that's a bit easier to use, more simple. And I'll make sure that they end up in the framework, and I work myself on the kite design tool, so basically parameterized meshing and then structural analysis, including the load cases as I discussed yesterday. So that will be part of it, and I think bringing these people together would be really nice, but I'm not really sure how I can do that, because I would love to hear more ideas that people have, and I think it would be even better if the ideas that they implement, they actually say, hey, look what I did, can we edit? And then we see how we can do that. So yeah.
Yeah, that sounds good. Or maybe like if there's a forum where people could be discussing stuff, like Discord or on the GitHub page or something.
Yeah, I think you can suggest. I think you can put it's like an issue, but you can put it like with a label that says, for example, improvements or suggestions. I think you can definitely put it there. It's for everyone to see. Also, if you have any questions on actual implementation of the code, or you find an error, put it as an issue so I can fix it. But then also other people can see the problem, because we had a problem with using it for the newer Matlab versions, and yeah, that's now fixed. But that was also put on Zoom. So also when I answer questions, everyone can read the same answers. It sort of becomes a big FAQ.
Very important, use the issue tracker of GitHub. Don't send Dylan an email, use the issue tracker, assign it or not assign it, and put a label on that. You can choose, as you explained, and in this way everyone sees it, and we can nicely manage this, and it becomes a forum actually, and you see what people want, and we can then even prioritize in the end. But of course, Dylan is not the developer of this. You are more the maintainer now with your own personal interest project, but it should become really a community effort, I think.
Hopefully,
yes. Hopefully, yes. There was.
I wanted to ask, this is now based on a hypothetical AP4 large-scale system that has never existed. But now, since there will be hopefully the AP3 flying soon, would it make sense to also have another version with a 100 or 150 kilowatt kite doing the same thing?
I'd say yes. It would definitely be useful. I actually have it implemented, the AP3 kite, as in the design specifics, as much as I got them from MPix before they filed bankruptcy. But so I never got the validated kite, which was the initial idea, and then implemented. So I do have it. We have some ideas somewhere with this Rishi study to see in his analytical model and compare, like, because he actually makes also the analysis of the AP3, and there's a lot of things balanced, I think, based in that model on the AP3 to compare that with something that can actually be reproduced, because he has dynamic simulations of the AP3 but done by MPix. So basically you cannot redo them, so you can only see the results. And with this framework, if we implement the kite, you can actually reproduce the results. So there's definitely the idea to do this with a smaller kite, but I have to see a little bit how this works, because I, to be fair, have no idea how this works with the IP, because some of the IP went to Mozero and some, I don't know. I have no idea what I can do with this kite now. I have it on my computer, but it's basically where it's there now, somewhere in a closet, somewhere in a folder.
Well, maybe in a year they would be to share that more. Let's see.
But it would be super nice also to have a smaller kite. First of all, it's easier usually to implement, but it's also to show a more realistic comparison with once they have flight test data, if they fly the tethered kite over.
I think that's exactly the role of Airborne Wind Europe to motivate the follow-up company of Ampix to actually make that available.
And maybe we can also eventually implement.
Yeah.
We might be able to implement the small-scale box kite eventually, because that one I do have a lot of data on. Working together with Kite, and they're providing a lot of stuff for me, which is very nice. So I might be able to also compare it with some flight test data. It's just a bit hard because it's a controller, so I basically need to get rid of the controller to compare. But we can implement a much smaller scale, low power, just as benchmarking. I think as much reference kites as we can get at the moment is actually not that bad of an idea until we get to a fully detailed something you could actually build. But
Thanks.
even a soft kite, but that's not my side. But yeah, I would love to have that too.
Thanks for the presentation. As we are now talking about producing open source and community available tools, could it be envisaged to maybe translate this in Python as it is free and available for everyone, open source?
I'd say once we have, I think Omid's conversion to the Matlab file is already the first step to go indeed to a language which would be open. I'd say use C++ over Python because it's much faster, but and that still allows you to also include it in Matlab if you want in Simulink. If you, and I think there's even a way to also include that in Python. But definitely, like it's a very good idea. I am not having the time to convert it to a Python code, but I have nothing opposed to if people are willing to convert it to another language, and then we can publish that together in the repository as well. So you have like basically both options. Because I think you're right, Matlab is expensive. Usually the universities have the licenses, but companies might not.
Yes, obviously it will take a lot of time, but nowadays there are tools that are coming, like you can, I mean, ChatGPT is already a great tool that can ease the process, maybe translate it to another language. So.
Yeah, I think that's why I think the Matlab file version of the code is the first step, because from there you have the code. You can actually indeed use like a ChatGPT to help you speed up the conversion between two languages.
But I think so it's a call for the community to pick that up.
But it's definitely, it has always been an idea, but it just never had come to that point. But I think, yeah, with now the files coming as well, I think we can speed this more up to use it in a language which is accessible to everyone. I agree.
And the second point is, of course, MegAWES is also a reference model. So there is really the design of the kite and the simulation framework. And the design of the kite is being used also by other tools like Orbbox and so on.
I think it is still maybe a good idea to at least the kite. Now, like let's say all the mesh details is in a Matlab file, because that is, like, was better efficient in terms of the memory at the time. But if that would be in a file that is actually open, that you can open by another software, would be nice. So that I should actually export to another file. But
Yeah, indeed.
Okay.
Thank you.
Any other question? No? Then thanks again.
yeah.